animal kingdom, the symmetry of an animal's body is often an indication of the animal's complexity. Animals display line symmetry, such as insects are usually more complex life forms than those displaying rotational symmetry like a jellyfish. Okay, so we're going over, Landerman has it.
No, I don't have a cup there. Thank you. Can I take it back after I'm done, or you want me to bring it during 4th hour?
When you're done.
Okay.
Okay, so over here you have this line symmetry, okay, through the center. In this one, in this jellyfish, it is rotational symmetry, so I could rotate each section of that and get the same thing over and over again. Alright, so a figure in the plane has line symmetry if the figure can be mapped onto itself by a reflection in a line called the line of symmetry. Okay, so you have that reflection line. Okay, we have this reflection line, so that line that we kept talking about before in section 1, okay, where we would reflect each point of our pre-image over that line to get the image. That's the same thing as your line of symmetry. You guys need to come to class on time. Alright, so below here, state whether the object appears to have line symmetry. Right, yes or no. If yes, draw all lines of symmetry and state their numbers. So we have to state how many there are as well. So in letter A, this crab here, okay, there is, I understand if you get this, but work on the assignment then and stop talking. There is one line of symmetry through the center of that crab. Okay, so if I were to split it horizontally here, it wouldn't flip over onto itself. So that's kind of what you have to look for. So that one is a vertical line. So there is one line of symmetry. Okay, so for this starfish then, we do have this vertical line here, this diagonal line, another diagonal line, another one, and another one. Okay, so we have multiple lines of symmetry for this one. So since there are 5 points to a star and all of them are congruent, okay, that means there's going to be 5 lines of symmetry. So if you have a regular polygon, you're going to have multiple lines of symmetry. Okay, so for this one, this is yes, and it is 5 lines. So don't just write yes or yes and no. You do need to state how many lines there are. For letter C, I can't draw in a line of symmetry for this figure here anyway. Okay, if I were to try and draw one, say this way, it would fold over and it wouldn't be the same on both sides. Okay, so this is no lines of symmetry. Okay, then letter D. Are there any lines of symmetry in letter D? Are there any lines of symmetry in letter D? No. You can't fold it this way. It won't map to itself. You can't do it this way. It won't map to itself. The only way you might be able to is diagonally, but you're still going to get it where it's kind of like this. Okay, so if I were to fold it along this line here, this part would come up this way, and then fold back that way so your corners wouldn't line up. Okay, so this one is no lines of symmetry. What about letter E? Letter E. How many lines of symmetry? 1. Through the center and vertical. And then letter F, how many are there? 2. 2. Vertical and horizontal. Not from corner to corner. Okay? The only way you can do that is if it's a square. This is not a square, it is a rectangle. Okay? So you can't say a line of symmetry is diagonal. Only way you can do that is if it is a square. So this has 2 lines of symmetry. Okay, so those are our lines of symmetry. Next, I do want to go into rotational symmetry. Okay, so a figure has rotational symmetry if the figure can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure, called the center of symmetry. Okay, so in the figures below, we have rotational symmetry because we can have a rotation of 90, 180, and 270 that maps the figure onto itself. So below here, looking at this 90-degree rotation, your center of symmetry is in the center of your figure. Okay, so you do need to locate that center of symmetry. Here, 90 degrees would be from one corner to the other. And if I were to take just this section right here and rotate it another 90 degrees, I would end up with this section here. Okay? Same thing with 180. So if I took this section here, okay, and I rotated that section another 180 degrees, I would get that remaining piece of that figure. So these do have rotational symmetry. If I were to rotate it a certain amount of degrees, I could get that entire figure. Last one is 270. Now this one would overlap if you were to rotate it. Okay, so if I have 270 degrees of that figure, that would be right here. Okay, so this section. Now if I were to still rotate that whole section 270 degrees, it would still map out onto itself. Okay, so you're still creating that same figure no matter which one of those degree measures you turn it. So that's kind of what we're looking at when we're looking at rotational symmetry. Questions on that? Yes, Hadley?
You can have like all of them, like you can have 90, 180, and 270, or it's just like...
Yes, you can have 90, 180, and 270. 0 won't go anywhere, so there's that. And this 45 at the bottom, don't count that one. That one won't map out onto itself. That's why I started with 90. So on the back, we do want to state whether it has rotational symmetry. Okay. If yes, we want to locate the center of symmetry and state the order and magnitude of the symmetry. So we want to state the degree measures that it could have for rotational symmetry. So in letter A, you do have to kind of change your thinking a little bit. If I could cut a slice out of your figure, can I rotate that piece around to get that one whole figure? Okay, that's kind of what you have to look at. So in letter A, we do have rotational symmetry. Okay, the center is in the center of your figure. I could cut out this slice right here and rotate it around that center to get that entire figure. Okay, so how I would go about doing this, I would take 360 degrees, right? That's all the way around. And I would divide by how many sides it has, because each side is this segment right here. Okay, so if I were to rotate it to here, that'd be the same segment. To here, same segment, same. Okay, so we want to take 360 and divide by how many there are. Okay, so in this case there are 6 sides. So I can start off with a rotation of 60 degrees. Okay, so each time I rotate 60 degrees, I'll get that whole entire figure.
Do you have Tanner Fromm in here?
No.
He's absent? Okay, thank you.
So from here, we can say that this has rotational symmetry. Of 60 degrees. Now what we want to do is just keep adding 60 degrees. Okay, so if I were to take another section of this, okay, and I have this whole section then, I could take that whole section and I could rotate it around that center point and still get that same image. Okay, that degree measure would be 120 degrees. So I could rotate that 120 degrees all the way around and get the same image. From here I'm going to add 60 to that. Okay, to get 180 degrees. So again, that's just adding on an extra piece there. And I could take that whole section and rotate it 180 degrees. Okay, is that kind of making sense? A little bit? Okay. I could then still add on 60 degrees to that to get 240. So just adding another triangular section there from the center. And then the last one will be 300 degrees. So you do need to state each of those degree measures. Okay, don't just write, yes, it has rotational symmetry and do nothing else. You have to write out rotational symmetry of however many degrees. Okay, questions on letter A? All right, letter B. Do we have rotational symmetry in letter B? If I took any part of that, will it rotate around to get the same image? No. Okay, so this one would be none. Okay, so you can always try and locate that center. So the center of this one would be here. I can't take a slice of that and rotate it all the way around to get that same figure. What about letter C? Yes. Okay, so here's your center. I could split this in half and I could rotate it 180 degrees. Okay, so I could take this section and rotate that entire section 180 degrees all the way to the other. Okay, so this does have rotational symmetry. And it is 180 degrees. Okay, so 180 degrees would be your rotational symmetry for that one. All right, I want you guys to do D and E. So state if it has rotational symmetry and then tell me what are the degrees for that rotational symmetry. I don't have a blanket, I'm sorry. All right, so looking at letter D, okay, to this flower, there are 5 petals. The petals are supposed to look the same, okay? I know in nature, not all of the petals in a flower are congruent, but on this picture, they are. So I could take one of those petals and rotate it a certain amount of degrees to get the rest. Okay, so since there are 5 of them, we can take 360 and divide it by 5, since 360 is the entire circle. Okay, so that will be 72 degrees. Okay, so we will have a rotational symmetry of 72 degrees. We'll add another petal to make it a little bit larger, so we'll add 72 and 72 to get 144 degrees. So we could rotate it 144 degrees to get the same. Add another 72 degrees to that. So we'll get 216 degrees. Add another 72 to that to get 288 degrees. Now you stop when you add 72 and you get 360. Okay? We don't need to state that 360 degrees is a rotational symmetry because it'll just map out onto itself. But you do need to state the other degrees. Questions? All right, so what about letter E? It does have rotational symmetry. Okay, so your center, again, center of the flower. Now with this one, you do need to be careful. Okay, because I only see 3 sections that I could rotate. Okay, so there's that larger petal and then the smaller one right next to it. Okay, so that would be 1 section, and then you could rotate that over and that over. Okay, so in this one, we're going to take 360 divided by 3, since there are 3 sections of the same thing around in that circle. So we'll have rotational symmetry of 120 degrees. And then adding one more to that of 240 degrees. Okay, so of both of those, we could have rotational symmetry for both of those. Questions on this rotational symmetry? All right, so on the side there, we have point symmetry. A figure has point symmetry if the figure can be mapped onto itself by a rotation of 180 degrees. A playing card exhibits point symmetry. It looks the same right side up as upside down. Okay, so it has that point symmetry if it rotates 180 degrees. So kind of like letter C up here. So C would also have point symmetry as well as that rotational. Now at the bottom we are going to go over this symmetry in 3-dimensional shapes as well. Okay, so plane symmetry is a 3-dimensional figure that can be mapped onto itself by a reflection in a plane. Okay, so you're reflecting in that plane in a three-dimensional figure. Okay, and then axis symmetry is a three-dimensional figure that can be mapped onto itself by a rotation between 0 and 360 degrees. So it's kind of the same thing that we did with your line symmetry on the front, similar to plane symmetry. And rotational symmetry is the same as axis symmetry. You're just doing it in three-dimensional figures. Okay, so below I do have some examples of three-dimensional figures. Okay, we want to state whether the figure has plane symmetry, axis symmetry, both or neither. Okay, so in letter A, could I reflect part of this figure over a line to get the same thing? I can. So if I go through the center of this figure, okay, so if I reflect over that line through the center of that figure, I would have that plane symmetry. Okay, you kind of see that? So if I only had part of that, I could reflect it over to get that other part. So we do have plane symmetry in this case. What about axis symmetry? Could I take a piece of this and rotate it? To get the same thing over and over again? No, I can't. So this is, we don't have axis symmetry. Okay, so no axis symmetry, just plane symmetry. All right, so letter B. Letter B. Do I have plane symmetry? So if I took a plane and I reflected a piece of this 3D image over it, would I still get the same thing? Yes, I would. So I could split this down the middle here. Okay, so I could take this section right here and reflect it over that plane to get the other side. I could also go in the center of this, right here. Reflect over that plane to get the bottom half or the top half. Okay, so I have two plane symmetries. Okay, so I have a symmetry that's vertical, a plane that's vertical through that figure that I could reflect over. I also have a plane that's horizontal that I could reflect that bottom piece to get the top piece. Okay, so we have two plane symmetries. Okay, and then what about axis symmetry? Could I take a chunk of this and rotate it around to get the remaining pieces? Yeah, you can. All right, so on the top here we do have our center of rotation. I could take each of these pieces, so this piece here, and rotate it around to get the other sections. Okay, so it's like taking a slice of that entire thing all the way down. We'll rotate it all the way around that axis. Okay, so we do have axis symmetry. And again, I want to state those degrees that I could rotate. So we'll take 360, which is the total amount of degrees, and divide by how many pieces I could make. So 5. Okay, so we'll have axis symmetry of 72 degrees, 144 degrees, 216 degrees, and 288 degrees. So again, I'm just adding 72 degrees onto each of those to get the next slice. So again, I do want you to write out those degrees when you have either rotational symmetry or axis symmetry. What about letter C? Do I have plane symmetry in this three-dimensional figure? No. Do I have axis symmetry in this three-dimensional figure? No. So we don't have plane, and we don't have axis. So this is neither. All right, last one is the letter D, so this baseball bat. Do I have plane symmetry in a baseball bat?
Can I grab some paper? No? Yes. Thanks.
Do I have plane symmetry in a baseball bat? Well, I don't if I vertically cut it, right? What about if I cut it horizontally through the center? Slice it all the way through the center horizontally. I could reflect it up onto itself then. So we do have plane symmetry. And that would be that horizontal slice. Yes, there is. All right, what about axis symmetry? There is axis symmetry. So if you go from the top of your baseball bat and in the center of the top part, you could take any slice and rotate that all the way around to get the same thing. So your axis symmetry will be any angle between 0 and 360 degrees. So this is 4 angles between 0 degrees and 360 degrees. So if you notice you have a circle, okay, a circular piece on anything, you could rotate that 1 degree and get all the way around. You could rotate that half a degree, get all the way around. You could rotate it 32 degrees and get it all the way around. Okay, so that's why this is for angles between 0 and 360 degrees. So if you see that circular piece, it's going to be between 0 and 360. Okay, questions on plane symmetry or axis symmetry?